third law of thermodynamics, standard molar entropies, and then start talking about the second law of thermodynamics also. Remember, the first law was our energy conservation law. It told us that total energy is conserved, right? If something loses energy, then something else has to gain that same amount of energy, and vice versa, right? Total energy change is equal to 0. The third law, and I know we're skipping the second, we will come back to it, I promise. The third law of thermodynamics. And honestly, we already know this one. You don't know it as the third law of thermodynamics, but what it says, you already know. What it says is that the entropy of a perfectly ordered crystalline substance at 0 Kelvin is 0. So remember, 0 Kelvin, that's absolute zero, right? It's as cold as something can possibly get. If it's 0 Kelvin and temperature is a measure of average kinetic energy, it has no kinetic energy, right? It's not moving. There's no particle motion. So remember, as particle motion increases, entropy increases. This has no motion, so no entropy due to temperature. And then perfectly ordered, remember, if there's only one way to achieve a state, right, perfectly ordered being that state, then my entropy is 0. And we talked about that in the last video using the Boltzmann equation. So the entropy of a perfectly ordered crystalline substance at 0 Kelvin is 0. So the entropy of a perfectly ordered crystalline substance, right? The reason we're saying crystalline is our other types of solids, remember, amorphous, just by nature, they're not perfectly ordered. So to be perfectly ordered, it is going to be a crystalline substance. At 0 Kelvin, right? That's not okay. That 0 Kelvin is 0. Right? It has no entropy, it has no disorder. It's perfectly ordered. So entropies are measured a couple different ways, or determined a couple different ways. The first one is using the Boltzmann equation that we already talked about. Again, remember, we were solving for entropy, not entropy changes. Unlike enthalpy, we can actually measure for entropy. With enthalpy, we had to measure a change, right? Is heat energy coming into the system? Is heat energy coming out of the system? With entropy, we can actually measure the disorder. So entropies are determined a couple ways. First one, using the Boltzmann equation. And then the second way is actually experimentally, and generally it's determined using heat capacities. We're not going to calculate it in either one of these ways. I just want us to be aware that we can determine entropy versus just entropy changes. From those entropies, however, we can then calculate our entropy change. So experimental data, sorry, I'm getting ahead of myself here. Experimental data. So kind of the key is we can, I guess when I say we, it's going to sound like we are going to do it, but entropies can be measured, right? Not just changes, as with enthalpy, right? We used standard heats of formation, right, to be able to determine the enthalpy of our reaction. And the standard heats of formation were also changes, right? They were delta HF with the not symbol instead of just HF. So with enthalpy, it's only the change we generally measure. With entropy, we can actually measure the entropy instead of just changes. Once those are determined, they're put into a table, and then we can use them to calculate things. So what we're going to do is we're going to use standard molar entropies. Standard again because it's at standard state. Molar entropies because they're going to be per mole. to determine the entropy change of our reaction. And this is also in that appendix that I posted on Canvas, so Appendix G. And standard molar entropies, that's an R, is determined as the entropy of 1 mole of a substance at standard state, so at 1 atmosphere and 25 degrees Celsius. So this time something that's in its standard state is going to actually have an entropy, right? Unless we're perfectly ordered at absolute 0, then its entropy is 0, they're all going to have entropies, right? Something like oxygen we talked about in a previous video, for its enthalpy change, right? Standard heats of formation is an enthalpy change, so we're making O2 from O2, so the change is 0. Here we're just saying what is the entropy, so we are going to have values for these ones. But then we're going to use it to figure out the entropy of our reaction. And it's going to be a very similar formula to what we've seen before. So it's going to be the sum of our standard molar entropies. I should have wrote that up there. S naught for our products minus the sum for our reactants. An example for us, and we'll use the same equation that we used when we were determining our enthalpy change. So C2H4 ethylene plus 3 oxygen going to 2 carbon dioxide plus 2 water. And my water, my carbon dioxide, everything is a gas. And then you don't need the 1 there, but there is a 1 in front of my ethylene. And then again, you would look up values, or I would give them to you. So you would look up your values in Appendix G. I'm just going to list them here. So for C2H4, let's make a little table. So S naught. And then my units on it are going to be joules per mole Kelvin. So for this one, 219.3. Since I put the units at the top of my column, I don't have to write it every time. For oxygen, 205.2. Again, it's not 0 this time, right? We're not talking about a change. We're actually talking about its disorder, right? Carbon dioxide, 213.8. And water, 188.8. These also are these are going to be positive values. So when we plug them into our formula, there's less sign mistakes. So that's always good. So, not H, S. So it's still just going to be sum of products minus reactants. Remember, we do need to multiply by those coefficients. So we do need to know that there's 2 moles of carbon dioxide and 2 of hydrogen. Sorry, 2 of water. And then 3 oxygen and 1 C2H4. So I need to multiply my number for carbon dioxide by 2. And then add to that my number for water. And then that goes in brackets. And then from that, we're going to subtract the sum for my reactants, sorry. So 1, mathematically you don't need that 1 there, but I want to put it there just so if it's not a 1, you don't forget to do it. 205.2. And then we'll grab our calculator. Still typing in, sorry, it's taking me forever. And I got a negative 29.7 joules per Kelvin. So again, it's just going to be the sum of our products, right, minus the sum of our reactants. Make sure you multiply that with the number of moles that you have. That's what this N is in here. I might not have pointed that out before, but that's what that is, right? My number of moles. So be sure to do some practice problems on these. There's some on the worksheets that are posted on Canvas. And then in the homework, there's a problem on entropy change calculation and enthalpy change calculation from standard heats of formation. So I said we're going to talk about the second law of thermodynamics also in this video. So second law of thermodynamics. And I started out this chapter by saying kind of one of our goals was to determine if a reaction would occur or not. And we said that a reaction will occur if it's spontaneous, right? Spontaneous is a reaction that if you just let it go, or a process, doesn't necessarily have to be a reaction, that will occur on its own without an external influence. The second law is our law that actually has criterion for spontaneity in it. It's the only one that we have that actually has criteria for spontaneity. So according to this law, in any spontaneous process, the total entropy increases. So in a spontaneous process, total being key here, increases. So again, remember the total is both the system and the surroundings, right? Delta S total. We could also call it delta S of our universe. Both of those work. We did the same thing with the first law, right? Our total energy is the same as the energy of our universe. The universe is the total. Sometimes it's written as total, sometimes it's written as universe. Honestly, I do use both. And remember that that is equal to my entropy of my system plus the entropy of my surroundings. Didn't fit it in there very good. And we know if our reaction is going to be spontaneous, according to this law, that's going to increase. So delta S total, right, or delta S of our universe, however you want to say it, is going to be greater than 0 when spontaneous. So if something is going to become more ordered, then something else needs to become even more disordered, right? With energy, it was conserved, right? If we throw energy in here, delta E total equals 0, right? So if something's going to lose energy, something else is going to gain the same amount. Here, if something is going to lose entropy, something else has to gain even more than the thing that lost, right? Because total entropy increases. So delta S, right? My entropy change total, so of the universe, right? System and surroundings is greater than 0. You have a spontaneous reaction. If our entropy change total is less than 0, it's going to be non-spontaneous. The opposite of a spontaneous reaction is always non-spontaneous, and vice versa. So if it was going from the forward direction and then in the reverse direction at the same rate, right, if we're at equilibrium, then my entropy change is actually going to be 0. So let's just say it was like a negative 80 joules per mole in the forward direction, then it would be a negative 80 joules per mole Kelvin, sorry, I got my units mixed up, in the reverse direction, right? The values are going to be the same because it's the same reaction, just the opposite sign. So if we're at equilibrium, right, if it's going back and forth at the same rate, remember that's what defines equilibrium, then my entropy change is going to be 0 and we are at equilibrium. So to determine if a reaction is spontaneous or not, we need to be able to calculate the total entropy. So we need to be able to determine the entropy of our system, right, our reaction, and then the entropy of our surroundings. So the entropy of our reaction or our system, right, those are going to be the same thing. We can just use those standard molar entropies that we just used. So we can determine this using standard molar entropies. So that's where we got our values for the reactants and the products from the table. And then we did the sum of the products minus the sum of the reactants, not forgetting to multiply the corresponding entropy by the number of moles of that particular substance. Right? And the reason we have to do both, right, is it's total, right? To figure if it's spontaneous, we need the total entropy. And remember, the total is going to literally be the total. It's my system plus my surroundings corresponding changes. So to get the system part of it, we can use standard molar entropies. To get the surroundings is a slightly more complicated process. So there's going to be two factors that factor into that. And I'm going to just give us the equation, and then we'll kind of work backwards to talk about the equation. But delta S of my surroundings is actually going to be equal to the negative of my enthalpy change for my system divided by temperature. It's hard to measure the surroundings, but what we can do is use system data to be able to determine the entropy change of my surroundings. So based on the enthalpy of my system, we can then get information about our surroundings. So the negative sign in front of delta H, right? Remember, if there's a negative, right, that means that heat energy is released and it's going somewhere, right? Remember, and heat energy is a form of energy, and energy is conserved. So if my system is going to lose it, the surroundings are going to gain. So any loss by the system is a gain by the surroundings. So because it's negative, heat energy is lost by the system, but the corresponding amount, we should say and the corresponding, I meant to get the eraser. Wow. Sorry, guys. It doesn't seem to want to go away. So, okay. If it's negative, heat energy is lost by the system, and that amount is gained by the surroundings. And what happens to something's entropy when it gains heat? Because remember, delta H is heat. So what we're saying is that my surroundings are getting warmer, right? Remember, if we have our hands on something that's exothermic, we can feel that heat. So when the temperature of our surroundings increases, what happens to its randomness? Yeah, it's going to increase, right? Those particles are going to start moving faster. So if we have an exothermic system, our surroundings are going to have a corresponding increase in entropy. So this gain in temperature increases the entropy of the surroundings. So the two are proportional, right? Negative delta H of my system is going to be proportional to delta S of my surroundings. It's also inversely proportional to temperature, and that one's maybe a little harder to understand, but we're saying that if the surroundings have a low temperature, then adding heat to it is a big change. If it has a high temperature already, then adding heat to it only makes a small change, right? So if you have a lot of something to begin with and you add a little bit more, it doesn't make a big difference. If you don't have much to begin with and then you add more, it makes a big difference. So it's inversely proportional, right? It's on the bottom of this. So inversely proportional to temperature. So if a low temperature to begin with adding heat has a big effect. If it has a high temperature to begin with, adding heat doesn't have that big of effect. So adding heat doesn't have a very large, that's a Y, believe it or not. So inversely proportional to temperature. So my equation, right, the entropy change of my surroundings, so I'm back up to this one, is going to equal to the negative of whatever my enthalpy change of my system is divided by temperature. So our equation, if we were to put it together, my total entropy change, again, if you want to put universe here, that's fine. That's going to be equal to delta S for my system or reaction, whichever version you want. The reaction is our system, plus delta S of our surroundings. This is how we had it written above. And then I'm just going to rewrite it, substituting in our negative delta H over T for surroundings. So delta S total is equal to my entropy change for my reaction plus the negative delta H reaction over T. So an example for us, we're going to calculate delta S total for a reaction that has an entropy change of 35.6 joules per Kelvin and an enthalpy change of negative 85.5 kilojoules. And then our question, is this reaction spontaneous, non-spontaneous, or at equilibrium? Remember, if it's spontaneous, we're going to get a positive value for our answer. If it's non-spontaneous, it'll be negative, and if it comes out to 0, it's at equilibrium. So we're really just plugging the numbers into this equation. We do want to be careful, though, about units. And then, oh, we do need temperature. Hang on. I forgot our little knot symbols. That's going to tell us our temperature, right? Remember, those knot symbols tell us that it's at standard state. So we are at 25 degrees Celsius, which is 298 Kelvin. So that'll be my temperature. It doesn't need to be in Kelvin. We're going to have unit issues, right? Because my entropy change is joules per Kelvin, our units will have to be Kelvin on our temperature to cancel. The other thing we're going to have to be careful with is entropies are generally in terms of joules. My enthalpies are generally in terms of kilojoules, and we're going to add these together. To do that, we have to have the same units for them. You can convert them both to joules or both to kilojoules. It really doesn't matter which. I am going to convert my entropy to kilojoules versus my enthalpy to joules. The other thing that's worth mentioning too is a lot of times on tests and quizzes, instead of typing in delta S not subscript reaction, like it's kind of a pain in the butt. I actually type in the word entropy, which turns out to be way harder for students, so be careful to read the name carefully. It's not always going to say delta S and delta T. It could actually say entropy change and enthalpy change. They look pretty similar if you were kind of hurrying or get nervous, so just be careful to know which one's entropy and which one's enthalpy and not get them mixed up. So my equation, we'll just write it down here so we don't have to keep scrolling up. Delta S for our reaction, which is just given to us in the problem. I am going to do unit conversion, however, plus negative delta H for my reaction over T. So I'm just going to move my decimal place over 3 places, right? There's 1,000 base units in a kilo, so I'm just going to move this over 3 places. So I'm going to have 0.0356 kilojoules per Kelvin, and then plus a negative. Now there's a negative in the formula, be careful. There's also a negative in the number. So this first negative is because it's negative delta H, and then the second negative is because my value is negative. And then my temperature, 298 Kelvin. So again, just be careful for the signs. This negative right here is part of my formula. So negative and then plug in delta H. Delta H just happens to be negative, so be careful. I see a lot of just sign problems when students are doing these. So I'm grabbing my calculator. And I got my total entropy change to be 0.3, I'm just looking at sig figs here. I'm going to have 3 digits after the decimal point. So 0.322, nope, 3, sorry. We'll talk about sig figs here in a second, because we're adding and we're dividing in the same problem. So this part, when I divide that out, I got 0.2869. Well, and I'm just writing down some of the numbers. This has 3 significant digits in it, and this has 3 significant digits in it. So when I divide that out, I want 3, so it ends right here after the 6. If you wanted to round after each step, 0.287. And then when I add these 2 numbers together, this has 4 after the decimal point. This has 3 after the decimal point, so I want 3 after my decimal point. And then my units on that, joules, kilojoules, per Kelvin. So is my reaction spontaneous, non-spontaneous, or at equilibrium? Yeah, spontaneous. I hope that's what you guys are thinking. Remember, it's spontaneous when entropy increases, right? When it's a positive value. So this is a spontaneous reaction.